issue is if it's not connected. But if K is connected, you look at GT module and you look at all vectors which generate a finite dimensional space under the action of U of K, enveloping algebra of K. K at. Then on those spaces, you can define the action of the group K, which is simply connected. If it's not simply connected, then you throw away the components which are not liftable to your group, and then you have to show that this is G invariant, but this is more or less formal. So it's an exercise, but you can, and then if K is, so in this case, this is a submodule of this guy, and in most cases, of course, it's zero. But if K is not connected, then you do the induction from identity components to the bigger group. So using these two things, you improve the resistance. Okay. And since, yeah, I mean, we are doing this, remember that at some point I said that this category, no condition, is good for homological algebra. For example, it has enough injective objects, so there is no problem in defining it. And the cohomological dimension of this functor is finite, so it lives between 0 and right functor P and then A1. Now, let's see how this is used to define cohomological induction. And I will do it in the situation where we need it. We take our flag variable, we take a point x, and we have a corresponding v of x. This is rel. Some algebra. Then it contains a cartan, which is sigma stable. It is a sum of eigenspace plus 1, eigenspace minus 1, and to this T we attach the subgroup, the centralizer of T in K, and we get our T. And now let's take
T, big T is the centralizer, little t.
Oh, yeah. So that this is its Lie algebra. Yeah, T is abelian, and let's see.
Wait, you're taking capital T is the group corresponding to little t, or is this the
group
corresponding
to capital T is the group. Oh, okay. It's a centralizer of all C intersected with K.
You mean little t?
Little
t is just
little t is the eigenspace, but if you take the centralizer of all cartan in K, you can get few components, but the Lie algebra will be the centralizer in K of C, and this will be T, Lie algebra of T. So this is the Lie algebra.
I see. It's C.
Yeah. I'm sorry. So
I know people think about it.
Lie algebra. Yeah.
Sorry.
I mean, this is a minor issue.
So, Dragan, what's sigma in this picture?
What?
What's sigma in this picture?
Oh, sorry, sigma is Cartan involution. So our Lie algebra of K are fixed points of sigma in G.
Just some inclusion.
Yeah. So you take maximal compact, you complexify it, and its Lie algebra is fixed points of Cartan involution. I mean, this is how you get it geometrically, but essentially the only thing you needed is fixed points of an involution. This gives you a Lie subalgebra, and K is some algebraic group with its algebra. So this is, I don't remember if we were still there, we proved that the pair GK and if K corresponds to evolution, there's finitely many orbits, so the machinery works in this case. So now, what I can do, I can construct the following module from U B of X, U of G, say A, where A is an element in M C T. And we extend to B of X by making, by N of X acting trivial.
What's the action of Dx?
The action of T is T sits in the Borel subgroup, so it fixes the point X, and we just want that the group action, when I differentiate, the action of T agrees to restriction of this T in here.
How does that Bx act on U of G?
Bx contains C.
How does that act on U of G? You're from UBX, UG to A.
I mean, yeah, or UBX acts by left multiplication here.
Or you
And on A, it acts by this.
So is this like a co-induced functor? Are you doing like algebraic
Yes,
co-inductive?
yes, but and then I am taking T finite part, and you're right, this is co-induced, but to explain the history, you should think of this. Let's assume that I have a vector bundle with fiber A at the point X. That formal Taylor series on flag variety would determine elements of this. Because basically you can differentiate it by any element of the enveloping algebra, and because Bx is the stabilizer, they will satisfy this. And Zuckerman's idea was, so these are formal Taylor series of sections. We don't know in general how to describe the global sections. So his idea was, now let's impose this K finiteness. K finite sections should be then something which corresponds to convergence. See, the problem was that Langland's conjecture was that you can take G mod T, and which is non-compact complex manifold. You take L2 cohomology on this, and on the L2 cohomology groups, you get discrete series. This was like his idea. Rel Veil bought. But I mean, this leads you to a lot of analytic difficulties because you're dealing with non-compact manifolds and you have differentials which define these forms, and you don't know that the images of differentials are closed. And when you take the cohomologies, they're infinite dimensional spaces with non-Hausdorff topology, it's total mess. Just take forms which I know. Very tricky analysis. So Zuckerman's idea was, let's replace this L2 condition by defining Poincaré of it is exact. So, I mean, here you take a T finite part of this form.
Why are we taking the T finite part?
I mean, just to be in this category.
Yeah, but like, why not the K finite?
I mean, this thing is still exact because T is reductive as K, and now, and if you think about this Foreman-Taylor series, they will behave well with respect to.
Because T is inside of K.
Yes. Yes.
Or T is inside of B as well, right?
Yes. Yes. So T acts on A. Yes. If you drop T, then T structure on A is completely irrelevant. And T, another thing I should mention, the T acts here by adjoint action. I mean, there are a lot of little things one has to check, but they are kind of straightforward. So you take this and then you compose with this. And this is, so these factors are called derived cohomological induction. Again, at the moment, it's completely unclear why, but you will see this at the moment. So now,
well, I don't know. For me, when I see this, because I know that like if you take this co-induced functor, if you take the G finite vectors in it, that's the same thing. It's just geometry. You're just geometry.
Yeah.
So this is like we're not doing all the way to G. We're just going to K.
Yeah. Yeah. So I mean, this is, we are going to denote this by IP of corresponds to the C and which is sigma stable and R plus, this is positive root system which corresponds to B of X and A. Now, I mean, this will, I can formulate duality theorem. And duality theorems, I mean, there is no way we can calculate the cohomology of irreducible Harshadder sheaves. But duality theorem tells us what is cohomology of standard Harshchandra sheaves. So Q is an orbit, tau is a connection. We take cohomology of this on X, and we take Harshchandra dual. This is why there is duality in the name, and this is equal to S minus P C R plus. So we take the point X in the orbit, and this gives us V of X, and our connection, which is a V module on the orbit Q, gives us the representation of C, which is just in general a bunch of copies of lambda plus rho, which comes from the twist, and also the stabilizer gives us a representation of tau. But this is, and then so we get U is the representation of C tau determined CT, sorry, determined by tau, and then you take its Harshchandra dual and tensor over C with geometric fiber of the canonical bundle on X at that point. So this gives us a cohomology of the standard sheaf, the standard Harshchandra sheaf in terms of cohomological induction.
Right, just bigger. So you basically you're saying you have some orbit, you have some vector bundle with connection on it, and you're taking the fiber at some point, and that gives you just restricted to the action of T. That gives you some T module, and that's what you.
Yeah, it gives you. I mean, first of all, since orbit acts by a bunch of copies of lambda plus rho, and then you have the action of T, which comes from the fact that this point has a part of the stabilizer is in K, and therefore T is in the stabilizer, so T acts on the.
But I think this is earlier. Capital T is actually fixed. It's actually it could be disconnected.
Yes, like he has those two R's. And the number of the corresponding group. So in the case the group acts transitively, cohomological induction is the same as sheaf cohomology, and this was Zuckerman's inspiration. He was playing with this construction, and then he realized that he gets this formula, so he thought to construct a Harshchandra model. Of course, this worked fine instead, and this construction is very nice for cohomology. Then look through what these representations are. I mean, this duality theorem gives you the connection which D modules here.
Is that just the same thing as like G mod BX dual?
Yeah, I mean, this is just a C corresponding to 2 rho, to the sum of positive roots.
C?
Complex numbers with the action of the
not omega 1, it's omega top.
Yes.
Oh,
Yes,
okay.
yeah, I'm sorry, I
No, it's
change the notation anyway you want. No, this is the canonical bundle, I think I said it.
Sorry, you probably said it.
Yeah, no, yeah, so it's exactly modeled to fit Serre's theory. You just have to use two different cohomology theories in general. Another remark, I mean, this gives us the formula for these cohomology standard sheaves. And one thing I want to mention, because this will play the role in our final example, that in the case when our Borel V of x is defined over R, cohomological induction is the same as standard parabolic induction and higher than right functors of zero. So this is the extension of this notion. I mean, you can formulate this in not for Borels, for parabolics, and define the same thing. I don't want to go into this, and then you get general parabolic induction, and if parabolic subalgebra is defined over R, then you get classical induction, but for these other parabolics, you get all kinds of strange things. And now I'm going to discuss this example of SU21, which is sufficiently general to see all the steps in the proof, but it's not trivial as SO2R. So this is a great place to start.
Excellent time to go to SU21.
Okay, thank you. G is SL C. So it's root system A2. Well, that's denoted by J, this matrix. Then the Cartan involution is sigma of T is J E J. So the K is a 2x2 matrix of complex matrix. And here you have negative trace of A. So that this is in SO3C, and K is equal to, say, B, which is B is in GL2C, and 0, 0, 0, 0. And here is the determinant of the universe. And now, so there are two Cartans. One are diagonal matrices, which say AB A times B inverse bottom, and this is in K. So there is, say, P in K, which we will refer to as a compact Cartan, because if you look at this real group SU21, this corresponds to Cartan subgroup, which is packed. And the other Cartan, so the V algebra I would denote by T, and the other one is C, which is not compact, which is A 0 B 0 minus 2A 0 B 0 A. where A and B are complex. So this is, let's call it maximally split. So in this case, C is, let's see how to name this. I cannot call it T, no, I didn't name it. So it has two eigenspaces. This one, I mean, this is the plus one, this is the minus one, there, one there. The orbit structure, I mean, remember how the orbit structure is determined. You look at the action of the normalizer in K of your carton. And so to describe this, let me just look at the dual of carton T. So this is the star. And if I look at the roots there, this is another thing I have to mention. So this is T is in K. So there are root subspaces with respect to T which are in K. So if G alpha is in K, then we say that the root alpha is compact. And if G alpha is not in K, then alpha is non-compact. I mean, this is just in the first case, Cartan involution maps alpha into alpha, and the other alpha to negative alpha. And these compact reflections with respect to compact root take a positive root system, which determines Borel in one orbit, into positive root system in the same orbit. So they keep the orbit invariant, but non-compact do not. So basically you have 6 positive roots, but if this guy is compact, then these chambers correspond to different orbits. And these 3 on the other side map into this. So if I take a positive root system corresponding to these orbits, I get 3 closed orbits. Why are they closed? Because in this case, the flag variety is flag variety of K, so it's projected, its image is in X projected. So I have C plus, C0, and C minus. They're one-dimensional closed orbits. And they're usually called, I mean, of course, here this, because in these cases you get complex structure on corresponding coordinates, so it's called holomorphic. One is called non-holomorphic, anti-holomorphic. I mean, this depends on the choice of complex structure. So basically, depending on your choice, you get this, and it's a non-homomorphic. This is just dimensioning if you look at various examples using this rule. And they all correspond to the Cartan subalgebra T. So remember, there is a surjective map of conjugacy classes of Cartans. Then there is this, say, C, which is maximally split. And there are three orbits corresponding to this. Q, which is open. And let's put here Q plus. So this is three-dimensional. And there are two-dimensional orbits, Q plus, Q minus. So this is the orbit picture, and closure relation is this guy contains these two in the closure, this guy contains these two in the closure, and everything is in the closure of the open orbit. So this is the orbit picture. Now, let's see what we can say about representations. So let me look at picture. So first of all, I want to describe discrete series. So discrete series are representation of sphere integral matrix coefficients. And what I claim that they correspond to these three closed orbits. So now let me draw a picture. Of course, these closed orbits, the Cartan is a two-dimensional torus. So this condition that lambda plus rho is differential of the representation of the torus tells us that the connection tau on these orbits exists only if lambda plus rho is a weight. So rho is a weight, so if lambda is a weight. And now let me draw the picture. This is, I hope I can do a decent job. I'm terrible at this. So this is a different color. So let's assume that these are our simple roots. So these upper three roots are positive roots. So negative chamber is this one. And in negative chamber, we have connections on the closed orbit. So, yeah, for all weights, and weights looks like this. I will leave it to your imagination. If you want, I can send you the pictures did on the computer, better than this. So, what is the point? If I have a closed orbit, now I have to recall the thing we are discussing. Closed orbit is of codimension 2 in the full flag variety. So if I take the standard module to closed orbit and I want to calculate the n homology with respect to Iwasawa n, this is what we discussed last time, we have to get contribution on the open orbit. The zero localization has to live in open orbit. And we discuss, when we discuss intertwining functors, that applying simple reflection increases the dimension of the support by 1. So if you look at this picture, for example, let me look at this guy, the easiest. I apply one simple reflection, and I get from this guy, I get, with respect to this root, I get this guy here. And then in the second step, I get this guy over here. So to go this way, I need 2 steps, and the same thing is here. So that I can get contribution to n homology at open orbit at best at these points. And possibly here. Agree? Now, I am on the open orbit. On the open orbit, so let me just draw a diagram. This is a different carton. So we can identify, we have to identify these roots. These are roots corresponding to this other carton. And on the other carton, we said that alpha is a real root if sigma alpha is minus alpha. It's a imaginary root. If sigma alpha is alpha and it's complex, this is different than alpha and minus alpha. If you calculate this for open orbit, then the middle root is real and this guy is C. So, if you look at these possible weights, they are, in this case, here. So you see the projections are on the positive part of vector part of the carton in a direction of real root. So now I have to remind you that by carton in decomposition, G naught is K naught times negative chamber of A times K naught. So this is carton decomposition. And A minus is negative chamber in A, Iwasawa A. I mean, this is also G naught is A naught, N naught. This is Iwasawa. And one can prove, I mentioned this last time without the proof, if I look at power series expansion of matrix coefficients along A naught going, A naught minus going towards infinity, then from these Harish-Chandra expansions by this result of Hasselmann and myself, the leading exponents are the minimal weights of n homology. And here, for example, in this situation, restricted to A, I have, these are possible weights, these two definitely are in, so this is the restriction to A, and this restriction to A is in a positive direction, so along the A minus, which correspond to this direction, the action of linear form is negative. So this means that the matrix coefficient is decaying and it's square integral. I mean, this requires some analysis, and I can give you precise references, but basically this is the idea, that this has to be negative in this direction for matrix coefficient to be square integrable. So you get that these representations are square integrable. Let me point out that if I this holds, let's see, if I am in the wall, then first reflection gets me here in this wall, and then the second reflection doesn't move me. So I get a weight which is not decaying but not increasing at this point, and this means that the matrix coefficients are tempered. Whatever the tempered means in L2 plus epsilon G. And this is something important in harmonic analysis groups. So basically what you see that these points, regular points, correspond to square integrable representations. The points in the walls corresponds to tempered representations, and they can be either zero or irreducible. So if say in these cases one of the simple roots is compact, the other one is non-compact. If you are in a compact wall, then global sections vanish. If you are in a non-compact wall, they do not vanish, and therefore these representations are these limits of discrete series. So this is what you, in a non-homomorphic set, both simple roots are non-compact, so you get limits on discrete series in both walls. And in anti-homomorphic, you have a dual picture. So along one wall, everything disappears, and in the other wall, you get limits of discrete series. So this is a special, so this tells us what happens with these orbits. So I'm going to discuss the other three orbits now, but we are going to see that for them, there are no square integrable representations at all. So this implies the following theorem. The original due to Harishchandra. So that group G naught as discrete series if and only if rank of A naught is equal to Dragan of G. Of course, this condition is automatic is SU21, otherwise I wouldn't be discussing this. But the second part of the theorem is, I mean, our version of this is so a discrete series are given as gamma x I u tau for closed orbits q in x. Okay, this is notation is bad because I mean, one thing I should mention, and this is a little bit of calculation, to show that actually the stabilizer in SU21s are connected. So for any lambda, we have exactly one connection tau. You cannot have more than one because the stabilizer is connected. So the action of the Lie algebra, which is given by lambda plus rho, determines tau. Of course, here, since I mean t is connected, that it has to be a weight, but to each weight we attach one connection, and therefore we attach one discrete series representation for any closed orbit. So modulo exhaustion, this proves Harish-Chandra's theorem. So now we are going to discuss why there are no square integral representations attached to these three non-closed orbits, and we are going to see what kind of representations attached to them.
So can you just
yeah.
What does discrete series mean?
Discrete series means that matrix coefficient of the group in L2 of the group.
Oh.
So this is a growth condition on matrix coefficients. Since these matrix coefficients on A are given say A naught minus as given by, I mean, in this case, this is actually classical. If you look at, say, take a root, real root alpha, then A in coordinates e to the alpha are just positive reals, and this is, say, A 0 minus. And you get, for matrix coefficient, a system of differential equations. One variable, I mean, if you embed this in complex plane, it has a regular singularity here, and these Harish-Chandra expansions here are nothing else than power series expansion around this regular singularity. And the systems, or say if you write it as differential equation for the Casimir, second order differential equation, it has two roots of initial equation in general, or maybe more. The center is bigger than generated. But anyway, we have a regular singularity here, and the leading exponents around, for expansion around 0, determine behavior at infinity. So the square integrability condition you can interpret as the inequality for these leading exponents. So what is the real part? And this is exactly this piece here corresponds to our A minus. So if my leading exponent is somewhere here, then the matrix coefficient will be square integral. If you do the calculations, requires writing down these measures in the conditions. So, and if the limiting case is this, when the leading exponent is this, and this corresponds to pair. So that's this. Okay, so now let me look at the other cases. If let me dispose the open case because this is the simplest one, and then at the end I will. So if I have an open orbit and I look at my roots, and in this case, this is a real root. I mean, now this is attached to the Cartan. So these two correspond to Cartan subalgebra C, which is one-dimensional vector part, one-dimensional toroidal part. The toroidal part goes in this direction, and these two complex roots. Now, if I look at the negative chamber, where when we take normal sections of our standard modules, I have integrality with respect to the stores. So I will get standard module for parameters which will, there will be lines here where I can get our standard modules. And wherever we are, the parameter with in this direction will be positive, and matrix coefficient will go to will grow. So this won't be, there is nothing here which is square integrable. The only situation when you can get temperedness is the origin, with the real part of lambda is equal 0. So here, of course, since lambda had to be a weight, it has real values here. In general, on A, in A direction, there is no condition, just condition on P. So there can be an imaginary part of the parameters. So here I have a family parameterized by imaginary numbers attached to this point. So just the real part of lambda is 0. This is tempered. But nothing else can be tempered, and especially it cannot be square integrable. So there are no square integrable representations attached to the open orbit. Okay, so now there is the last case, because these two orbits dual, Q plus and Q minus. So let me draw the picture. So here I will assume this is real, and these are complex groups. See, going from these orbits to this one is accomplished by one complex reflection with respect to this root, which switches these two, and R comes into it. I mean, there are formulas for the dimension of the orbit, so you can check this. If you think about this, you will see immediately. This is the right answer. So now let me look what happens in this case. So this is my positive chamber. And this is A direction. This is toroidal direction in this carton. So here I have, in toroidal direction, I have condition, integrality condition, but in A direction I have no condition. So it's something like this. It's a very bad picture. And now, what happens if I'm on two-dimensional orbit? So to get to open orbit, I have to apply one complex reflection. So I am applying reflection with respect to this root, and I'm flipping these guys. And say, if I take a picture here, I will get something over here, and the corresponding component in zero-end homology in A direction will be on the negative side, so it will grow in negative direction. So there is no square integrable representations. Here you can have temporary representations possible. So this completely proves Harshchandra's theorem. I mean, the square integrable representations can come only from these closed orbits, and for regular, yeah, I should put it for closed orbits and regular. So this takes care of classification of discrete series. And I mean, it can look kind of technical, but if you look at Harishchandra's work, I mean, his proof is much, much more complicated than this, because he constructs explicitly the characters, discrete series, which has some distributions on the group, and shows that this is the discrete part of Plancherella formula and discrete part of Plancherella formula by some general theory from functional analysis corresponds to discrete series. So there's, I mean, this proves, the proof is much shorter and in some sense more elementary. But how do you get the rest of alignments classification? So first of all, okay, let me draw a picture, and then I will discuss alignments formulation. If you look at the pictures on the board, then I mean, with a little bit of imagination, because my picture is really bad, if you move this chamber over here, then these lines should align. And also you will have a picture for Q minus, which you could map here. So if you look at these three pictures, then you get a picture like this. Okay. Okay. This. And so this is, let's see. This chamber corresponds to this one. See, the real roots is on the top, and this one is sideways. So let's put, say, a triangle here. This is this guy. And here you have the dual picture for CP minus. So you can lump these three pictures to a picture one picture which corresponds to this Cartan C. So this looks not like something particularly appealing. But now, if you look at this picture, here, Cartan evolution maps R into minus R. So, okay, I'm saying this wrong. I don't want to look at Cartan evolution. I want to look at the action of conjugation defining real structure. And it preserves R. It acts trivially on R because R real roots correspond to roots in A. So it will also preserve those guys because it will be just it will just split them. There is no other option. So basically, the Borel define, I mean, one can explicitly calculate this. I'm just trying to give you some hint. The Borel corresponding to these three positive roots is defined over R. So, if I look at standard modules corresponding to these parameters, by duality theorem, they are given by a cohomological induction corresponding to a real Borel. And this is ordinary induction. So the consequence, when you lump all of this together, is that these representations are induced by in classical terms, by the representation of minimal parabolic subgroup, which is in this case Borel. So what do we see? We see we have discrete series, and these representations, which correspond, tempered representations, appear here. So, formulation of Langlands' classification in his paper is the following, that you get all representations by taking tempered representations and then taking really induced representations from parabolic subgroups. When on the Levy factor, you have an irreducible tempered representation, so you assume that you know those. And if the A parameter is negative, say in quotes, then this representation has a unique irreducible sum. Actually, Langlands had a weaker description of this formulation in his mind, that here you have unique irreducible sum. From D-module theory, you can easily see that. And these are Langlands representations, so these are non-tempered. And then the work of Knapp and Zuckerman described the structure of tempered representations. And here, we basically reprove this, because if you use the irreducibility theorem you mentioned, you can see in this case that irreducible tempered representations are either these limits of discrete series or irreducibly induced representations at these points or with arbitrary imaginary lambda, and you know exactly when these things reduce and how they reduce from the module picture. For example, I can show what is kind of very intriguing example, that the limit of discrete series for this orbit, so the thing which corresponds to 0, is the same representation as this unitary induced representation here. And this was kind of a surprise, because Costa had the conjecture that matrix coefficients of discrete series are rational, and then this would imply that the functions that need matrix coefficients on a matrix coefficients of limit discrete series were rational. And in this case, it's easy to show that this cannot happen here, looking at these differential equations. You see that you have log terms in the asymptotic expansion. So this observation that these representations are the same play a role there. And of course, the fact that they are the same depends, it is the consequence of the fact that for singular infinitesimal character, equivalence of categories fails. And we kind of understand how it fails, but this is still kind of mysterious, and you have to do calculation in each possible case like this. There's no some kind of nice categorical description of what happens in general, which is important. So this is this example, and I think my time is also up.
Let's first thank the speaker for all the lectures.
Thank you for your patience.